Good evening. My job is to set the framework for Professor Cristiano Giammani, who is visiting us here for 2 weeks, who will be speaking about the formation of black holes, the so-called primordial black holes in the early universe. And these black holes are formed due to what are known as enhanced perturbations on small scales, often assumed to be generated during inflation. And the task before me in the lecture today and tomorrow is to introduce you to inflation and cosmological perturbation theory. It is possible that you're familiar with a good fraction of these topics, and this is aimed at non-specialists. Here is an outline of my talk. I will speak initially about inflation, as to why we need inflation. And then we will talk about perturbation. Inflation is introduced, as we will discuss, to resolve the so-called horizon problem, which is a problem associated with hot Big Bang. The beauty of inflation is that it not only helps you overcome this horizon problem, it also allows you to explain what are known as the small anisotropies that are superimposed on the smooth cosmic microwave background. I will explain this as we proceed. And the perturbations, we'll classify them based on the transformation properties on a constant time hypersurface. Remember, we are in a cosmological situation. And they can be classified as scalars, tensors, or vectors. Vectors are not generated during inflation, or even if they are generated, they decay quickly. So we'll be talking about scalars and tensors. We will derive the equations of motion governing the perturbations. So we'll initially understand how they evolve at late times, and then we go on to discuss how they are generated during inflation. And in particular, we will talk about the scalar and tensor power spectra generated in slow roll inflation. I will explain all these terms as we proceed. And then I will talk about very common knowledge, namely constraints on inflation from the CMB data. And this is where set up the idea of enhanced power on small scales through deviations from slow roll inflation for Cristiano. And it is this enhanced power on small scales that will be responsible for the formation of, increased formation of primordial black holes. Time permitting, I will sort of ensure that my lectures are self-contained. I will talk about, how what are known as primary and scalar induced secondary gravitational waves, I will explain these terms as we proceed, are generated in the early universe. Close with summary. I have to update the references. I hopefully do so tomorrow. A quick word on notation. H bar c is 1, and the Planck mass is 1 over root 8 pi e. And we will essentially be talking about a flat, spatially flat Friedmann-Lemaître-Robertson-Walker line element. T is my cosmic time. A of t is the scale factor. Eta is the conformal time coordinate defined in this manner. And dots are differentiation with respect to cosmic time. Times are differentiation with respect to the conformal time coordinate. H is my Hubble parameter. And often in the context of cosmology, particularly early universe cosmology, we will introduce another unit of time, the number of E-folds, n, and it is nothing but the number of E-folds is just you define this as dn by dt is h, which is a dot by a. Okay, and that's how you define the number of E-folds. And often, if you want to integrate your equations of motion numerically or even analytically, E-folds happens to be a very convenient variable. So why do we need inflation? Again, this is aimed at non-specialists, the first few slides at least. Okay, this timeline of a universe. This thing that has been indicated here is actually the manner in which the scale factor changes with time. So you are supposed to have had a Big Bang, And here there is a depiction of inflation where the scale factor is increasing very rapidly with time. And then there is a smooth change here, and there is a slightly different change and a change that you see towards the very end, close to today. So in the hot Big Bang model, you don't have inflation. You have an epoch of radiation domination and followed by an epoch of matter domination. And there is this time, known as time of decoupling, when essentially the photons interacting with matter and they start streaming freely towards us, and that is what is observed by one of these missions, the WMAP mission, as the cosmic microwave background. And this is a picture that you would have seen. What does it tell you? It is essentially much like the manner in which the Earth is projected through this ITAF projection on ellipse. The entire CMB sky coming to us from this time of decoupling, which is about 380,000 years or so from the time of the Big Bang, it has been projected on the sky. This corresponds to the entire 4 pi of the sky. What does these different dots represent? Different colors represent? They correspond to deviations in temperature, 1 part in 10 power 5 in different directions of the sky. Evidently, there are anisotropies, but there is remarkable isotropy, level of isotropy. The average temperature of the CMB is about 2.725 Kelvin. And on top of this 2.725, uniform background, isotropic background, there are small anisotropies that are superimposed. So we would like to know, why is the CMB so isotropic and how did these anisotropies arise? The hot Big Bang model cannot explain this for the following reason. I will try to explain this so-called horizon problem in a few different manners. If you had an epoch radiation domination, right, you need to have something which is smoother, not expanding like this. If you had an epoch of radiation domination until the time of decoupling, followed by an epoch of matter domination, you can show that the causally connected region at the time of decoupling, when the CMB starts streaming freely towards us, is just 1 degree in the sky. These are the white patches that represent the causally connected region in the sky at the time of decoupling. Within the hot Big Bang model. What is the hot Big Bang model? You have a Big Bang, we don't know what happened, followed by an epoch of radiation domination, which is followed by an epoch of matter domination. This is what the causally connected region in the sky looks like. So in other words, if there are different temperatures in different regions of the sky, separated by 1 degree, we would have been perfectly happy with the scenario. There are other issues, but well, it is a possibility. But we don't see that. What we see is a remarkable level of isotropy. And this is the challenge for cosmologists. How do you explain this extent of isotropy in the sky? Of course, you also have to explain the anisotropy superimposed on it. There is another way of understanding the horizon problem. So remember, this metric here is conformally flat. So in other words, if I choose eta to my time coordinate, the light cones in this description of the Friedmann-Robertson-Walker universe, whatever the scale factor is, are at 45 degrees. So I can draw a forward light cone, I can draw a backward light cone here from today to the time of CMB, to the time of decoupling to be precise. And then from the time of Big Bang, I can draw a forward light cone. You invert one of these light cones. And what you find, I would urge you to calculate this. You know the time, when the CMB comes to us from. I just indicated the time. And you know what is the age of the universe today. It's about 13.7 billion years. This is in terms of cosmic time. You need to convert them into terms of conformal time. And what you do is that this forward light cone is significantly smaller than the backward light cone. This is yet another way of stating the problem. How do you overcome this? Remember, if you have the scale factor, in matter and radiation dominated epochs, matter and radiation domination, what do you have? You have the scale factor behaving as t power half during radiation domination or as t power 2/3 during matter domination. I'll leave this as an exercise for you to work out. In all these cases, the conformal time coordinate goes from 0 to infinity. when t goes from 0 to infinity. Okay, and remember, what is my conformal time? It is integral dt by a of t. So the Big Bang starts at eta equal to 0. Okay, and therefore the forward light cone has to start somewhere here, and the forward light cone is not as big as the backward light. How do you overcome the horizon problem? Well, if you have an epoch of inflation, that will overcome the horizon problem. What is inflation? It corresponds to a period of accelerated expansion. Okay, I will let you think about it. How can inflation overcome the horizon problem? Inflation corresponds to a situation, as we will discuss in the next slide. I'm sorry about that. Corresponds to a case where a double dot is greater than 0. In a slide later, I will explain how inflation helps you overcome the horizon problem. What you can show is that if a double dot is greater than 0, the conformal time coordinate can be negative, and therefore you can push the Big Bang as behind as possible. And remember, the light cone are always at 45 degrees. So if my eta is sufficiently negative, so my forward light cone can be as big as the backward light cone to ensure I overcome the horizon problem. In fact, if you have power law expansion, it is straightforward to show, that eta will be negative when p is greater than 1. This is what you have, right? A is t power p. In the next slide, I will establish how you need a double dot greater than 0 to overcome the horizon problem. Okay, so what do you have? A double dot is just, if I use t power p, is p into p minus 1, p power p, and this is greater than 1 if p is greater than 0, not surprising. Okay, now what is eta? Eta is integral dt by a of t, right? This is proportional to integral dt, which is nothing but t power 1 minus p divided by 1 minus p. If p is greater than 1, eta is negative, and therefore what you can do is that by introducing an epoch of inflation in the early universe, very much depicted here, very much in the manner depicted here, what you can do is that you can push eta negative, you can push Big Bang earlier and earlier, so that the forward light cone is as big as the backward light cone, and you overcome the horizon problem. Why do you want a double dot greater than 0? Well, I mentioned earlier as to how, you want to explain not only the extent of isotropy of the CMB, you also have to explain the anisotropies that are superimposed on it. How do you study this? How do you study the manner in which, primordial fluctuations leave the imprints on the CMB? The good thing is that we saw that delta T by T, T being the temperature, delta T by the deviations of the extent of the anisotropies in the CMB, which is delta T by T, T being the average temperature, delta T being the deviation from the average, is 1 part in 10 power 5. Which essentially means delta rho by rho, rho being the energy density of radiation in the universe, is also of that amplitude. In other words, the perturbations are very small. And as a result, to understand the manner in which perturbations are generated in the early universe, how are they imprinted on the CMB, I can study using what is known as linear perturbation theory. I can assume that the perturbations are small. And what do we do? Well, what we do as we proceed with lectures is that we will write the equations of motion that governs these perturbations. I had written down the metric which corresponds to a smooth Friedmann universe. It is described by one quantity, namely the scale factor. We will later introduce additional quantities which describe perturbations. I indicated earlier as to how there are scalar and tensor perturbations. And we will introduce those different perturbations, and we will write equations of motion for those perturbations. And we will do that at the linear order in perturbation theory. And if I have linear equations, and I have a smooth, homogeneous background, this is what you do in quantum field theory. If you have linear equations and you have a smooth background, then what do? It's convenient to study them in Fourier space. And in Fourier space, these modes decouple, and you can study the evolution of modes separately. As long as the perturbations are linear, your quantum field theory is a linear quantum field theory. And that's what we will do. So there are two scales. When you study perturbation, there are two scales that are involved often. One is the wavelength of the perturbation or the wave number of the perturbation. And the other, in an expanding universe, there is another scale in the problem. What is that scale? I've already indicated that scale to you. It's the Hubble parameter. You can construct A dot by A, which sets a scale in the problem. So there are two scales. That is what has been indicated. In a log-log plot, we have plotted two quantities, the wavelength of the perturbations, but the physical wavelength of the perturbation. Because the Friedmann universe is expanding, the wavelength, physical wavelength of the perturbations is always proportional to the scale factor. Okay? The other scale, as I said, is the Hubble radius. You can calculate how it depends on the scale factor depending on the manner in which the universe expands at a given time, either during the radiation or matter-dominated epochs. In a radiation-dominated epoch, you can show that h is proportional to a squared. And therefore, in a log-log, remember, n happens to be logarithm of a. Okay, if you integrate this, you'll find that n is logarithm of a. You choose some value of 0 conveniently. We will talk about how we count the number of e-folds as we proceed. So it's just logarithm of a. Don't worry about the 0. So during an epoch of radiation domination, the Hubble radius, which is h inverse, a dot by a inverse, happens to have a slope of 2. I will let you work that out if you haven't done that earlier. The wavelength of the perturbation is always proportional to the scale factor. Okay? Now, notice, if you have an epoch of radiation domination, this has a slope of unity, this has a slope of 2, and as a result, at very early times, the wavelength of the perturbations are well outside the Hubble radius. The Hubble radius is the only scale that you can construct given A of t, right? And that roughly reflects the scale of curvature or the scale of a causally connected region. And that's, it's Hubble radius. And this wavelength implies that there is a wavelength of the perturbation which is much larger than the Hubble radius. And in such a situation, one of the important things when you carry out quantum field theory is what are the initial conditions on the perturbations. And when you quantize a field, the nature in which these initial conditions are chosen define what is known as the vacuum state of your quantum field theory. We'll talk about it, something known as the Bunch-Davies vacuum as we proceed with the lectures. So the wavelengths are well outside the Hubble radius. So you do not know, in the absence of an epoch of inflation, if you just had the hot Big Bang model where the radiation dominated epoch followed by an epoch of matter domination, you don't know what are the initial conditions that are to be imposed on the perturbation. So of course, Harris and Zeldovich, came up with this idea that, there should be no specific scale in the problem. The power everywhere should be the same. And amazingly, what we observe is something very close to it. But there are deviations from it. But what inflation does is that if you have an epoch of inflation, right? So as you go back in time, what you can ensure is that these modes emerge from inside the Hubble radius. So the wavelength of the perturbations should be inside the Hubble radius at an early time. So in other words, as you go back in time, minus d by dt, lambda p, which is the wavelength of the perturbation, d subscript h, which is the Hubble radius, which is a dot by a, has to be less than 0. In other words, this guy has to decrease faster than the Hubble radius if you want them to start from inside the Hubble radius, from a causally connected region at early times. And if you demand that, what you obtain is a double dot greater than 0. And if you have an epoch of inflation, what happens is that, as I indicated here, the conformal time becomes negative, right? I have here. The conformal time becomes negative, and you can ensure that the forward light cone as big as the backward light cone to overcome the horizon problem. In other words, this entire CMB sky is causally connected, and there is no issue with all of the temperature being virtually the same in all directions of the sky. So you need an epoch of inflation in order to overcome horizon problem if you want to explain the extent of isotropy of the CMB. But how do you achieve inflation? Well, I'll come to this in a minute. I'll come to the previous slide in a minute. So, you turn to the Friedmann equations. You should be familiar with this. Rho and P are the energy density and pressure associated with the source that is driving the expansion. And you can quickly convince yourself, if you don't want a double dot greater than 0, rho plus 3p has to be negative. And you can't do that with ordinary matter or radiation. Therefore, you need to turn to some exotic fields in order to achieve inflation. And well, one of the simplest such fields is a scalar field, and I will come to that in a matter of minutes. Before I go talk about scalar fields, I would like to introduce another way of understanding the horizon problem. What I have plotted here is the same figure as this, but with a little more details. And instead of the physical wavelengths, I have plotted what are known as the co-moving wavelengths. Okay, co-moving length scales. So there are two quantities involved. Again, the wavelength of the perturbation and the Hubble radius. But what has been plotted is the co-moving Hubble radius and the co-moving wavelengths. The co-moving wavelengths or wave numbers don't change with time. That's why they are called co-moving. Hubble radius I have indicated is A dot by A inverse. You divide by A, the scale factor A, to construct the co-moving Hubble radius. What you find interestingly is that if you have an epoch of inflation, you plot the co-moving Hubble radius as a function of logarithm of A, the number of E folds that I had indicated earlier. You can convince yourself it has a slope of -1 if you have what is known as de Sitter inflation. Okay? And during radiation domination, you will have a slope of +1. It will grow like this. But in the early universe, you can have very non-trivial epochs. Okay? You can have a primary reheating. You can have an epoch of radiation domination. You can have an epoch of secondary reheating and, epoch of radiation domination. Notice, to matter domination, there is a slope from this and this. This has a slope much similar to this, and that corresponds to the epoch of late time acceleration. Okay? And all these correspond to just different scales that we talk about today. This corresponds to the CMB scale, and this is the scale that leaves the Hubble radius at the very end, towards the end of inflation. The CMB is sensitive to what the dynamics during inflation over these early times. And what Cristiano will talk about, and I will also talk about later, is the dynamics during the later stages, which re-enter during the epochs of radiation domination. So let's move to scalar fields. So we are interested initially in a homogeneous field. We are interested in achieving inflation. How do we achieve A double dot greater than 0? So you take a canonical scalar field, construct the stress energy tensor, and then you construct the energy density and pressure. And the equation of motion of the scalar field can be arrived from conservation of the energy density associated with the scalar field, and you arrive at this equation. Okay, there is an error here. This should be phi double dot, unless the dot is not, visible. So what do you have? You want A double dot greater than 0, which means rho plus 3p has to be greater than 0, and which you can use these relations to immediately conclude dot squared has to be less than v of phi. Look at the equation of motion of the scalar field. If there is no h, if you are in flat space time, you would have had phi double dot plus v phi equal to 0, or phi double dot equal to minus v phi. It's like a particle. It's like q double dot equal to minus dv by dq. It's a particle flow, falling down a potential. All that happens in an expanding universe is that there is an additional frictional term that the field encounters. So the dynamics of the field is easy to understand. So it's clear that if you have a potential, if the kinetic energy of the field is small, you are guaranteed to have this condition. Therefore, you can have inflation. And even if you start with a large initial velocity, what often happens is that because of this frictional term, the field slows down and end up satisfying this condition. Kinetic energy is smaller than the potential energy. Often, if the potential has a minima, it is around the minima that this condition is violated, and such potentials naturally lead to the end of inflation too. So, what kind of potentials do you require? Well, there are many models in the literature, and this is one of the challenges faced by inflation. Many of these models, can easily permit inflation. Only a small class of models are actually ruled out by the data, as we discuss later. So this is what we will refer to as a large field model. We will discuss the dynamics as we proceed. We will discuss it analytically. And once they set up Mathematica, we'll, see how the dynamics occurs with a simple potential. A large field model is where inflation occurs, when the field is far away from the minimum. Okay. Well, the values of the field are also large compared to the Planck scale, as we will see within some example. There are some called small field models where it occurs when phi is much smaller than MPL. And then you have more complicated hybrid models where the field, first rolls down in one direction. There are multiple field involves, and it can roll down in another direction to generate, different epochs of inflation. We will encounter some of these non-trivial dynamics as we proceed. I mentioned earlier as to how, even if the field is starting with a large initial velocity, the frictional term slows the field down. And we want phi dot squared to be much smaller than v to achieve inflation. To be smaller than v, to achieve inflation. But what we will do is that we will assume something known as the slow roll approximation. We will not only assume phi dot squared is smaller than v, which guarantees inflation. We will assume, in fact, it is very small. So remember the first Friedmann equation, h squared is equal to rho by 3 MPL squared. The rho of phi contains a phi dot squared by 2 and a v of phi. We throw away the phi dot squared by 2 term, and therefore you are left with h squared is v of phi. This is one of the approximations we make. Remember that picture where we drew the backward and the forward light cones. Evidently, you need eta to be sufficiently negative if you want your forward light cone as big as the backward light cone. In other words, you need an adequate amount of inflation. Not only do you need inflation, you need inflation to last sufficiently long if you want to ensure that all the 4 pi region of the sky is causally connected by the time of decoupling. And you often hear the term you need at about 60 e-folds of inflation or so if you want the forward light cone to be as big as the backward light cone. So what it means is that not only should the velocity be smaller than v of phi, it has to remain sufficiently small for sufficiently long duration of inflation in order to lead to the required duration of inflation. As a result, what you do is that, remember, you assume this is phi double dot, it's a typo. Okay, you assume this is also negligible. The phi dot double dot is also small. Therefore, you are left with this equation with rho determined by v and this equation with 3h phi dot. The phi double dot term ignored, and you have essentially in the slow roll approximation, when the velocity of the field is small, then what you have is you just have to solve these two equations, and it becomes a very simple system, to solve. In fact, using these arguments, I really don't have time to construct these parameters. You can construct these so-called potential slow roll parameters. This parameter particularly is useful. So given a potential, I just have to construct this, and we will see that if epsilon v is smaller than 1, it is that part of the potential that will lead to inflation. And we will see some specific examples later. You can more formally construct a hierarchy of the slow roll parameters. Can I close this? You can construct a hierarchy of these slow roll parameters. N is the number of e-folds that I have introduced, and you can construct a hierarchy of them. And this is an exact relation. So what you can do is that you can rewrite your Friedmann equation and the equation of motion describing the scalar field in terms of the parameters. So it's a simple exercise. And you can immediately see if epsilon 1, we will quickly see that epsilon 1 being smaller than 1 corresponds to an epoch of inflation. Okay, and that is again straightforward to establish. So what do you have? Epsilon 1 is minus h dot by h squared. Remember, h is a dot by a. So it is a dot by a dot. Okay, so this is h squared minus 1 over h squared, a double dot by a, right? And then minus a dot squared by a squared. This is minus a double dot by a h squared minus plus h squared divided by h squared, right? So what essentially happens is that I have to take A double dot by A is equal to 1 minus epsilon 1. So if A double dot by A has to be greater than 0, epsilon 1 has to be less than 1. So what you will typically find, field starts at some point, epsilon 1 is small. As the field rolls down a potential, epsilon rises, leading to an end of inflation as field comes to the bottom of the potential. So in the slow roll approximation, what happens? This goes away, and you're left with these two equations. H squared is V by MPL, 3 MPL squared, and 3H phi dot plus V phi equal to 0. And what is amazing is that you can quickly integrate these two, combine these two to arrive at this equation. So what do I have? In the slow roll approximation, so what do I have? I have H squared, 3H squared, MPL squared is V, and then you have 3H phi dot is minus V subscript phi. Okay, what is phi dot? Phi dot is d phi by dt. I can write this as d phi by dn, dn by dt. Remember, the definition of the e-folds is logarithm of a, so dn by dt is nothing but h. So I have dh by d phi n. So I have this equation, 3h squared phi n is minus v phi. So I can divide one from the other. What do I have? I have 3h squared phi n divided by 3h squared MPL squared is minus v phi by v. Okay, this goes away, right? I can quickly, what do I do? This is d phi, this goes away. So I have d phi by dn is minus v phi by v, which I can immediately integrate to arrive at this. So notice in the slow roll approximation, all I need to do is that you give me your favorite inflationary potential, I can integrate this to obtain phi as a function of n. So what you can show is that, I mentioned earlier that in the slow roll approximation, this epsilon v is the same as this epsilon 1, which is minus h dot by h squared, I have written here. Okay, you can show that. I will leave it as an exercise for you to show. So what essentially happens is that you take a model like this, okay, a potential like this, and you construct epsilon v, and you see where it is 1. You find that phi e is this. What it implies is that it is very clear to, understand the form of the potential. The potential is just, I will draw it here. Right? So these are what are known as large field models. So you have a potential, which is behaving like this. Well, let us for simplicity assume n is even, so that, it's oscillating at the bottom of the potential. So you have a v of phi that behaves in this fashion, v of phi plotted as a function of phi by MPL. So you start somewhere higher here, the field sort of rolls down, okay? And remember, if you start with a higher velocity, the friction slows it down, and you're guaranteed to have inflation. And somewhere around the bottom of the potential here, phi e, which is of the order of MPL or so, okay, n times MPL, okay? So inflation ends. Inflation naturally ends in these potentials. And where is epsilon v? Much smaller than 1? It is clear, this is possible when phi by MPL is much greater than 1. You have epsilon v much smaller than 1, and that's why these are referred to as large field models, because inflation occurs when the field is far removed from the minima, in fact, when phi by MPL is much, much larger than 1. And as I mentioned, inflation ends somewhere here. And you can plug this in. You can plug this in here. So what do I have? If I write that expression, so I have n minus some ni, okay, which corresponds to some phi I to phi, right? D phi, V by V phi, right? If I have such a potential, oh, I should go to that. If I have such a potential, what do I have? I have d phi. V is some V naught phi power n divided by MPL power n. V naught n phi power n minus 1 MPL power n. This goes away. V naught goes away. Sorry. V naught goes away. This becomes phi, okay, some phi I to phi, which is nothing but phi squared by 2 minus phi I squared by 2, which is divided by n, which is equal to n minus ni. There is a factor of MPL squared that I missed out here. There is a 1 over MPL squared, right? MPL squared. This is not surprising. You need to have dimensions right. There is an MPL squared. So you can immediately, I have written it phi E rather than phi I, right? And phi E is the location where inflation ends in a simple m squared phi squared model that occurs at root 2 MPL. When n equal to 2, it occurs at root 2 MPL. And what you have obtained is you can obtain a solution as a phi as a number of E folds, you have arrived at a solution. Phi E. For instance, if you want to numerically integrate and you want 60 E folds of inflation, you know where to start. So you choose n equal to 2. This is what I wanted to show with the Mathematica notebook. It's straightforward to integrate in terms of E folds. You rewrite your exact equation. Remember, this solution is obtained in the slow roll approximation, but you can rewrite the equation, this equation in terms of the number of E folds, and you can integrate this in one line in Mathematica, and you find that this solution you obtained is a remarkably good approximation to the actual numerical integration. And what you can show is that if you start with some phi I of about 16 times MPL, it's reasonably larger than MPL, then inflation occurs for about 60 E folds, and inflation is terminated around this value, okay, and then the field oscillates at the bottom of the potential. And you can do a similar exercise for other cases too, okay. There is something called small field model. You have a potential something like this, okay. I will just illustrate the form of the potential here. So what do you have? You have a potential, which is like this. It turns like that, okay. So V of phi by MPL, right? And around, this starts, this is something like phi very close to mu. And you will be able to show that inflation occurs over this domain, and as it comes down, inflation is terminated. You can calculate the place where for Q equal to 2, for instance, and this condition when phi is much, much greater than MPL, you can calculate what is the value of phi E. It happens to be roughly close to mu. And you can arrive at the solution in the slow roll approximation by plugging in this potential in the earlier expression and carrying out that integral. And you can do this for a more popular Starobinsky model, which is described by this, by this potential. I would urge you to plot this potential, okay? So I will just draw it here for you. And I would also urge you to read about what is the origin of this potential, right? So this potential is like that. It goes and flattens out at large values of the field. It flattens out to V naught. So I'm plotting V of phi as a function of phi by MPL, right? And this value is V naught. And you can again, calculate where the end of inflation occurs, roughly where it occurs, and you can actually arrive at a solution to this in the slow roll approximation. And again, I can share this mathematical code, you can integrate this and fit this solution on top of it, and you find that it is a remarkably good agreement to the actual numerical solution. So I hope you have understood in simple models how simple models permit slow roll inflation. I hope given a potential, you will be able to determine where inflation occurs, and if the model permits slow roll inflation, how you will be able to arrive at the solution for the background. And here is actual numerical integration. So this is the Sriramkumar model that I have indicated here. And what this dots or blue dots and red dots have been plotted at equal intervals of time. What happens is the field moves initially very slowly, and then it picks up speed, and somewhere here it oscillates at the bottom of the potential. You enter a phase called reheating, which I will not have time to talk about. So this is the phase portrait. And what you have is something known as an inflationary attractor. What I should have done is drawn different, if you go ahead and draw different trajectories corresponding to different initial conditions, they will come and merge on this attractor. This is nothing but, essentially a damped simple harmonic oscillator where, it just comes down and falls into the origin eventually. And you are guaranteed to have inflation. You're guaranteed to have slow roll inflation in simple potentials. Slow roll inflation is easily achieved in many of the potential. The question is whether those models are consistent with the data. Something which we don't have to specify when you integrate this is the value of V0, for instance. Okay, and you will find that we'll discuss it as we proceed. It is fixed essentially by the amplitude of the perturbations, and we will discuss that now. So we have seen why we need inflation, how inflation is achieved with the aid of scalar fields, and we have discussed the dynamics of the scalar fields in some simple popular inflationary models. I mentioned earlier as to why we need inflation to explain the extent isotropy of the cosmic microwave background. But we saw that in addition to the isotropy, there are small anisotropies superimposed on it. And the question is, can inflation explain those anisotropies? Anisotropies are, if you go back you are looking back, remember this light cone that is drawn, right? So it essentially corresponds to densities which are different, delta rho by rho being the perturbations in the energy density of the fluid, the dominant fluid at the time being radiation, being different at different parts. They correspond to inhomogeneities on a surface which you are seeing now as anisotropies on the sky. So if you have inhomogeneities, remember our Friedman metric was homogeneous. The metric was independent of space. It was only dependent on time. So we now need to introduce inhomogeneities on it. And how do you impose these inhomogeneities? How do we study them? In order to understand that, it is important to understand the nature of these perturbations. Perturbations are deviations from homogeneity, essentially. And let's take a constant time surface in a Friedman universe, okay? Based on the manner in which these perturbations that I introduce in the metric behave under rotation, I can describe them as scalar, vector, and tensor perturbations. You will appreciate them in a couple of slides or two later. And the scalar perturbations are the dominant density perturbations, and that is what give rise to the largest imprints as anisotropies on the CMB, and they are responsible for the large-scale structure in the universe. Vector perturbations are essentially vorticity fields, okay? And since we are talking about essentially perturbations generated during inflation, there is only a scalar field present, it's not going to induce any vorticity fields. So we will not worry about the vector perturbations at all. Vector perturbations could be magnetic fields, for instance. But you can again show magnetic fields decay quickly in a Friedman universe unless you do something else to it. Tensor perturbations, you have heard about them, you know about them. They are gravitational waves generated in the early universe. And importantly, the gravitational waves can be generated even in the absence of sources. Even if I have nothing else, I have just gravitational waves in my inflationary background, they will be generated from the quantum vacuum. And these gravitational waves generated from the quantum vacuum are what we will refer to as primary gravitational waves. And the strength of these gravitational waves will depend on the model at hand, as we will see. And as I already mentioned, that inflation does not produce any vector perturbations. We will not worry about it. How do you arrive at equations generating the perturbations? How do you arrive at the equation describing the background? Well, you take the metric, plug it into the Einstein's equations. And in the same fashion, all you need to do is that you introduce perturbations in your Friedman metric, plug it into the Einstein's equation. You have perturbations on the left-hand side, perturbations on the right-hand side, and you arrive at equations governing these. That's all you need to do. And what we will see later, I may not be able to come to this today, we will discuss this later. The fluctuations are generated during inflation, and the fluctuations are essentially generated due to the perturbations are generated due to the fluctuations in the quantum field. The inflaton that we have, the scalar field that drives inflation, we have just talked about a smooth background. On top of it, there are fluctuations present. This is very early in the universe at high energies. They are intrinsically quantum in nature. They naturally contain fluctuations, and it is these quantum fluctuations associated with the scalar field that give rise to the primordial perturbations. We will discuss that tomorrow. Let's turn to understand what the different perturbations are. So you have a perturb metric. This is the perturb metric about the smooth background metric, which we have already seen. Remember, we can, talk in terms of their behavior under rotations on a constant time surface for convenience, for instance. So there is a delta G00, it contains no free index, therefore it's a scalar. Delta G0I contains one free index, therefore it's a vector under rotations, transformations on this constant time surface. Ij contains two indices, therefore it's a tensor. But I can use something known as the Helmholtz theorem, which you know. If I have a vector, I can put that as a gradient of a scalar plus a true vector. A true in the sense of it is transverse. It satisfies this condition. Right? Vorticity, for instance. Right? It's a true vector. You can, write a vector, vorticity satisfies such conditions such as this. So a delta G0I can be written as a scalar as a vector, gradient of a scalar as a vector. And similarly, instead of applying this logic to one index, I can apply this logic to two indices, I and j. When I do that, what I can do is as follows. I can introduce a scalar and multiply with a delta ij. That will give me a tensor. But what I do is that I remove the trace, I ensure that, the trace is only here. I write a scalar differentiated twice like this to get another tensor with two indices. Right? That's what it is. But what I have done, I have written in such a fashion, this is traceless. All the traces here. So I can use two scalar functions, psi and e, to construct a component of delta Gij. It is just Helmholtz theorem applied to each of the indices. And I can, just like I have a delta Ib, I can construct delta Ifj, where Fj is a vector to construct a delta Gij. Anything that cannot be written, just like anything that cannot be written as this, I dump it into Si. Anything that cannot be written in this fashion goes into Hij. So since I have already accounted for the trace, this is traceless and it is divergence free. Okay, you know what they are. We will talk about it soon. So now let's count the number of degrees of freedom associated with this scalars, vectors and tensors. So what do we have here? I have a which is delta 00. There is one scalar there. There is one scalar here. There are two scalars here. Right? So how many scalars do I have? I have 4. How many vectors do I have? There is Si. I goes from 1 to 3, but there is one condition, right? Okay. So let's count it in arbitrary space-time dimensions. Then it will become clear. And then we will talk about 4 space-time dimensions. If you are in d+1 space-time dimensions, what will you have? For how many independent degrees of freedom will Si and F have? It's I will go from 1 to D, but there is one delta I equal to 0, so you will have D minus 1, right? So there is a D minus 1 here, there is a D minus 1 here. There are 4 scalars, okay? All the remaining number of degrees of freedom have to be dumped in this Hij, right? So how many degrees of freedom does delta G mu nu have? It's D plus 1 into, it's a symmetric tensor in D plus 1 dimension. So it will have D plus 1 into D plus 1 by 2 number of degrees of freedom. That's what delta G mu nu has. All of them have to be in the 4 scalars, in the 2 vectors, and this Hij. Is that clear? Okay. So that's what I have. In D plus 1 space-time dimensions, I have 2 times D minus 1 vector degrees of freedom. Clear? Okay. And then after we impose the traceless and transverse condition, this Hij, remember, we ensured the trace is here and everything is transverse here other than this. Therefore, if traceless condition is 1, transverse condition is how many? D. Okay. So these correspond to D plus 1 conditions. I hope I got that counting right. So in D space-time, Ij can go from 1 to D because Ij are spatial indices. They go from 1 to D. So the number of independent degrees of freedom, the total number of degrees of freedom is of Hij is D into D plus 1 by 2. It's a symmetric D-dimensional matrix. That's all. But then there are D plus 1 constraints, traceless and transverse. So the number of independent degrees of freedom associated with Hij is D plus 1 by 2. I just, computed this. So I have 4 scalar degrees of freedom, okay? 2 into D minus 1 vector degrees of freedom and so many tensor degrees of freedom. You add all of them up, you indeed get the total number of degrees of freedom associated with delta G mu. We are in 4 dimensions, okay? So you have 4 scalars, right? And then you have 2 into D minus 1, so it is 2 into 3 minus 1, right? How many is that? 2 into 3 minus 1 is 4, okay? And then what do you have? You have, how many is this? It is 3 plus 1, 4. 4 minus 2 is 2. Sorry. 3 minus 2. I was counting. So it is 3 plus 1 is 4. 3 minus 2 is 1. 4 by 2 is 2. So Hij is described by 2 degrees of freedom. And Hij corresponds to gravitational waves. These are the 2 degrees of polarization associated with the gravitational waves. So gravitational waves has no other degrees of freedom associated with it, but there are scalar degrees of freedom. Now, I talked about the delta G mu nu in 4 dimensions, what is it? 4 into 5 by 2, 10 independent degrees of freedom. But there are also coordinate degrees of freedom, x mu. There are D plus 1 such coordinate degrees of freedom. Okay? So there are D plus 1 coordinate degrees of freedom. These are often referred to as gauge degrees of freedom because remember what are we trying to describe? We are trying to describe a metric which contains perturbations. It's smooth, but there are small perturbations on top of it. Right? So as I carry out a coordinate transformation, I should not allow these perturbations to become large. The perturbations should remain small. In other words, the coordinate transformations are not arbitrary. You can go from one coordinate to another, but those coordinates the transformation should ensure that the perturbations, amplitude of the perturbations remain small. This restriction on the coordinate transformations, are referred to as gauge transformations. Okay? You cannot carry out arbitrary coordinate transformation. You should carry out transformations that ensures the perturbations remain small. So there are D plus 1 such coordinate transformations. Evidently, I have to take some x mu to x mu prime. There is no tensors involved. That is why there are no further degrees of freedom associated with the gravitational waves, Hij, script Hij that I had. But I can carry out, using scalars, a time coordinate transformation of the time coordinates such as this, I can use a scalar delta x to carry out the spatial coordinate transformation. And I can consider, and therefore what do I have? And then I can have, there is something, okay, this should be delta perpendicular xi. So similarly, I can use a divergence-free vector delta xi. That should have been, there is an error in the slide, it should have been delta x perpendicular I, which means divergence of that is 0. Okay, so I can use such a coordinate transformation. I leave the time unchanged. I can use this coordinate transformation, this delta x perpendicular I, to carry out a coordinate transformation. So there is one scalar, another scalar here. This is divergence free vector delta x perpendicular I, that is d minus 1. So d minus 1 plus 1 plus 1 is d plus 1. That's the number of coordinate degrees of freedom in d plus 1 space time dimension. So I'm trying to ensure that all the degrees of freedom are accounted for. So now we started with, in the earlier slide, there were 4 scalar degrees of freedom and 2 d minus 1 degrees of freedom, vector degrees of freedom. But then there are these gauge degrees of freedom or coordinate degrees of freedom. So there are 2 scalar functions, delta t and delta x. I can use them to get rid of 2 of those degrees of freedom. Therefore, 4 minus 2 is 2 scalar degrees of freedom that you are left with to describe the perturbations in the early universe. And there is delta x perpendicular I, which is d minus 1 degrees of freedom. You had 2 times d minus 1 degrees of freedom earlier. I can use this to remove one of them. So you essentially have 2 scalar degrees of freedom in any space-time dimension. You have 2 tensor degrees of freedom, right, in 3 plus 1 dimensions. And if you are in 3 plus 1 dimension, there is 2 vector degrees of freedom. In the 3 plus 1 dimension of our interest, there are 2 scalar, 2 vector, and 2 tensor degrees of freedom. Tensor degrees of freedom corresponds to gravitational waves. We are not going to worry about vector perturbations because they are not generated during inflation, and there are 2 scalar degrees of freedom. There are 2 ways of studying this. Okay, all I have is that counting this again. I'm going to put up the slides. I'm going to make this slide available. You can take a look at it. You can do the counting and you can show that everything adds up nicely. And in 3 plus 1 dimensions, there are 2 scalars, 2 vectors, and 2 tensors. Now we need to arrive at the equations of motion governing these perturbations. There is a theorem that is known as the decomposition theorem. Okay, I will not have time to prove this. You can establish this. It is discussed, for instance, in Weinberg's book on cosmology. What do you need to do? You have discussed only the metric degrees of freedom, right? It's only the left-hand side of the Einstein's equation. You need to also discuss what happens to the source term, delta t mu nu. That's the first order perturbation in your matter fields. That is again another symmetric tensor, second rank tensor. Whatever you have talked about here on the left hand side applies to the right hand side as well. Right? So you can write your delta t mu nu in general in terms of scalar vector and tensor perturbations. And what the decomposition theorem states is that you have to only equate the scalar part on the left hand side to the scalar part of the right hand side, vector to the vector, and tensor to tensor. So if you don't have any what are known as anisotropic stresses, the tensors will satisfy a simple equation, source-free equation in a Friedmann universe, as we will see. Okay? I'm not going to talk about vectors, but scalars perturbations will have a source. For instance, if you have a scalar field in the early universe, they will have a perturbation, and that perturbation will act as a source for the scalar perturbations on the left hand side. So all you need to do is arrive at the equations of motion governing the perturbations, and because of the decomposition theorem, we can study them independently. I can study scalars separately from the tensors. Those are the only 2 things of our interest. So now we need to include scalar perturbations in my metric. How many true scalar degrees of freedom are there? There are 2. So I need to somehow include them in my Friedman metric that I had introduced earlier. There are two ways of studying this. One, you can choose to work in a specific gauge. That is what we adopt. It's simpler. Or you can construct, quantities that are invariant under these gauge transformations. You can speak to me if you are interested in them. I can point to some references. But for now, we will take the simpler approach of working in a specific gauge and arrive at the equations of motion governing the scalar perturbations. We'll come to the tensors later. So there are two scalar perturbations. I presume you can recognize them immediately. If you set psi equal to 0, phi equal to 0, it is the Friedman metric, FLRW metric that I had introduced earlier. So all you need to do is that you take this metric, phi and psi are perturbations, which mean in addition to time, they are also dependent on space. It is these perturbations that characterize the inhomogeneities in your Friedman universe. So all you need to do is calculate delta G mu nu, the perturbed Einstein tensor, and you can arrive at this left-hand side. And I mentioned earlier as to how you need to introduce the delta T mu nu as the source on the right-hand side. There are three possible sources, right? One is a perturbation in the energy density. Remember, I had energy density and pressure as far as the background is concerned. Now there will be a perturbation in the energy density. There will be a perturbation in the pressure. This is what is referred to as delta rho and delta P. And there is also a velocity perturbation. But since it's a scalar, it's a gradient of a scalar, right? So what it means is that, look, everything is smoothly moving with the expansion in the absence of perturbation. But if there are inhomogeneities, what it means is there will be something called peculiar velocities. They will not move with the expansion. They move in random directions. But that has to be constructed in terms of scalar because we are focusing on scalar perturbations. So it has to be a gradient of some scalar which we have called as delta Q. So therefore, I've constructed my delta T mu nu in terms of the scalar perturbations in the source, which are characterized by delta rho, delta P, and delta Q. And I can construct using them the different components of the delta T mu nu, and I just plug in on the right hand side of the Einstein's equation. I obtain all these. Now you can have something known as an anisotropic stress, that is the delta Tij can be not equal to delta Ij, which means I need to describe that term in terms of a two tensor, a tensor of rank 2. For instance, if you have electromagnetic field, it will have anisotropic stress. Okay? And then, but in the absence of such anisotropic stresses, I have just a scalar field, okay, in the early universe. If I have fluids with no anisotropic stresses, what is amazing is that the I not equal to J equation leads to this condition. So you started with two scalar functions to describe perturbations in the early universe. But if you don't have sources which possess no anisotropic stress, what does it mean? Delta T mu nu along the spatial part, Ij is diagonal. It contains only delta P, delta Ij. In such a case, you are left with essentially you can set phi equal to psi. These phi and psi are known as the body potentials. They describe the perturbations in the early universe, okay? And you are left with these equations. You can set phi equal to psi everywhere. And what you can do is that you can combine this equation and this equation easily to arrive at a simple equation for this body in potential phi. Okay. Note differentiation with respect to the conformal time coordinate. The script h is what is known as the conformal Hubble parameter. It's a prime by a instead of a dot by a. And we have introduced something called delta P and A. It's called the non-adiabatic pressure perturbation. It is just a definition of, it is just delta P minus Ca squared delta rho. What Ca is what is known as the adiabatic speed of sound. It is just Ca squared, just P dot by rho dot or P prime by rho prime. Okay. And that's what this is. So if you want to understand how perturbations evolve in the early universe, you just need to solve this Bardeen equation, that's all. If you want to understand how they evolved during the radiation-dominated universe, you need to know what is delta PNA. If you're thinking simple fluids which contain delta PNA, no delta PNA, you can set that to 0. Okay? And you just need to know what is H. You know what is H in a Friedman, in a radiation-dominated universe. You can solve this Bardeen equation exactly. And in fact, you can solve the Bardeen equation in a situation. You can see this discussed in Dodelson's book on titled Modern Cosmology. You can solve this Bardeen equation in a situation where you have both radiation and matter present, and you can actually, on certain scales, not at all scales, but in certain scales, you can solve this. But we will discuss the solutions to the Bardeen equation on what are known as super Hubble scales. I will explain that as we proceed. Before I discuss the solution to the Bardeen equation, I'm going to introduce something called as the curvature perturbation. I will explain this term as we proceed. Maybe this is a good time for me to start. I notice that I'm doing well on time. Okay, so I'll be glad to answer a few questions at this stage. I can take break for 2 minutes and answer questions. Are there questions? Yes. I need to describe the perturbations in some manner. In the sense of on a constant time surface, those are the most generic transformations I will have. No, we are not. Okay, I am describing the perturbations. I am interested in studying the evolution of the perturbation at different slices. So at any given time, I'm looking at a particular, yeah, exactly. And on that surface, rotations are a simple transformation, okay? And I classify the perturbations based on their behavior on this surface. Yeah, because I'm interested in the evolution of these perturbations at different time slices. Yeah. Any other questions? Okay, if there are no other questions, let me proceed. So I'm going to introduce a quantity called the curvature perturbations. The reason for this nomenclature, I will explain, it's explained here. I will come to that in a minute. So as you can see, it is a linear combination of phi and phi prime, of the Bardeen potential phi and phi prime. So what you can do is that you can take this curvature perturbation and then plug in this Bardeen equation. Notice there is a spatial difference appears only as nabla squared phi. This is because of the fact that your space-time is, the background space-time is homogeneous and isotropic. So therefore, the spatial dependence appears only as this, okay, in this form. Remember, you have a spatially flat Friedman universe. And therefore, what you can do is that I can study the evolution of these modes. I can just Fourier transform this Bardeen potential and study the evolution of these perturbations for each case separately. The equation of motion in Fourier space, all that will happen is that this nabla squared will pick up a minus k squared, okay, and there will be a subscript k appearing everywhere corresponding to the Fourier transform of these variables, whether it is phi or delta PNA. And therefore, if you are interested in phi subscript k, it is essentially the same equation with this replaced by k squared. So I have defined the R in real space. You can define that in Fourier space. It is just a Fourier transform of this quantity. It will pick up a k here, and you can plug this definition here, and what you obtain is this equation for this so-called curvature perturbation. What essentially happens is that, remember, you have the background is a spatially flat Friedman universe. You can take this metric that you had and calculate what is the 3 curvature on a constant time surface. and that happens to be nabla squared r. And that's why it's referred to as the curvature perturbation. In other words, the deviation from flatness of a constant time surface is characterized by r. It's inhomogeneous. And that is why the local 3 curvature on the spatial hypersurface is proportional to r, and that's why it's called the curvature perturbation. And it's a linear combination of the Bardian potentials. You can take this equation, plug in this Bardian equation, and arrive at this equation. And this is where I need to introduce this term called the sub and the super Hubble scales. Let me see whether I have the slide here. So I have to go back a few slides. Remember this picture. These modes are in super Hubble scales. What it means is that this is the wavelength, physical wavelength of the perturbation, and this is the Hubble radius. Here, the wavelength of the perturbation is larger than the Hubble radius. This domain, you say that the wavelength of the perturbation is on super Hubble scales. Here, it is in the sub-Hubble scales. If you have an epoch of inflation, if you don't have an epoch of inflation, at sufficiently early time, all modes of interest are on super Hubble scales. Something I didn't mention, but I presume you may be familiar with this. What are the wavelength or of interest? I will talk about it maybe tomorrow. So all scales of cosmological interest are outside the Hubble radius at early times if you don't have an epoch of inflation. If you have an epoch of inflation, what happens is that inflation allows you to bring the modes inside the Hubble radius. We will discuss tomorrow how you can impose well-motivated initial conditions on these perturbations. So they are inside the Hubble radius, they evolve to super Hubble scales, right? And they re-enter the Hubble radius at later times. So as far as late time cosmologists are concerned, all they want, for instance, what Cristiano will require for his discussion is what is the strength of these perturbations as they re-enter the Hubble radius during radiation dominant epoch. What I'm going to argue is that tomorrow is that how can you have enhanced perturbations on scales which are on, which re-enter the Hubble radius during the radiation dominated epoch. So again, to repeat, these are super Hubble scales and they re-enter the Hubble radius at late times. So let us understand the behavior of the Bardian potential and curvature perturbation on super Hubble scales. So what I'm going to do is as follows. I'm going to redefine, this is my curvature perturbation equation, and this is my Bardian equation. I'm going to introduce a different variable u, both dependent and independent variables. I'm introducing them for the sake of convenience. So what you essentially have is that Bardian equation reduces to a significantly simpler form if you write in terms of this variable. And now what I'm going to assume is that I'm going to have simple fluids, radiation and matter, which have delta P and A is 0. Okay? Then this becomes 0. And we are on super Hubble scales. What does super Hubble scale mean? That the wavelength of the perturbation is much larger than the Hubble radius. So the wavelength of the perturbation, super Hubble, super/sub. So what do I have? The wavelength of the perturbation, the physical wavelength of the perturbation is larger than the Hubble radius. This is super. Okay? Sub means the wavelength of the perturbation is smaller than the Hubble radius. Remember, this is just H inverse. So this corresponds to K much less than AH. Right? K by A is the physical wave number. Okay? And this corresponds to K much greater than AH. This corresponds to a situation where lambda P is larger than H inverse. Okay? This corresponds to the situation, the other way around. Lambda P is much smaller than H inverse, and this corresponds to the case where lambda P is much greater than H inverse. So this corresponds to K much smaller than AH. So what I can do is that I can simply ignore this term, And if you have power law expansion of the type that I had written, T power P or something like that, okay, then, power law expansion of this type for the scale factor, you can show that ignoring this corresponding to this correspond to the modes being outside the Hubble radius, okay. Then under these conditions, this is not there, and you can immediately read off one of the solution. UK proportional to theta is one of the solution, okay. And what you find is the following. Theta is given by this term. It's some strange combination of the conformal parameter and its time derivative. And what you can obtain is this solution. All I am saying is that the Bardian potential through a set of transformation in the super Hubble limit, you can arrive at two solutions like this. And the point to note is as follows, okay. This is a solution. One of the solution is where phi is a constant. Okay, it's a second order differential equation. There are two constants, Cg and Cd. And how do they have to be fixed? How do these constants have to be fixed? They have to be fixed by initial conditions, right? So let me explain. Go back. I should have made another copy of that slide. Okay, I didn't. So remember, you are here. You are solving a second order differential equations. There are two constants. What I am shown is that there are two solutions. One of them is a constant. The other one is actually a decaying solution. I will explain that. But if it is a decaying solution at late times, what will it be at early times? It will be very large. That's not possible. You are talking about perturbation theory, where the perturbations are small at early times. So you need a solution which is growing with time. It's not a problem. Okay. But if it's decaying with time, at early times, it will diverge, which means the perturbation theory will not be valid. That's why these coefficients are referred to as C growing. Okay, I've gone too far ahead. C growing and C decaying. And I will let you convince yourself as eta increases for expanding universes, this corresponds to a decaying mode. Okay. For, you need to determine what is gamma during a matter and radiation dominated universe, etc. It's not difficult to do. You can arrive at it. So essentially, I will ignore this. So I'm left with this case here. Okay. And now, remember, I drew this picture where the modes are outside the Hubble radius. But we don't know what is Cg of k. If I try to solve the Bardian equation on super Hubble scales and demand I have well-motivated initial conditions at early times that the perturbation theory is valid, all I can say is that this is 0. But I do not know what is Cg of k. In other words, I do not know what is the spectrum of the phi k of eta. And how do you generate that? This you generate during inflation. The perturbations are generated during inflation. The Cg of k is determined by what happens during inflation. So we will come to that, and that's why it's called the growing mode. The growing mode is actually a constant. So what do you had? You had a relation between r and phi, right, through this relation. So you plug that in. W is the equation of state during an expansion. It's 1/3 during radiation domination, 0 during matter domination, etc. You can quickly use this solution, plug in this expression for the Bardian potential, and show that R is essentially Cg of k. And as you go from matter to radiation to matter dominated epoch, on super Hubble scales, okay, you can relate Bardian potential during radiation dominated epoch through Cg of k potential during the matter dominated epoch on super Hubble scales. And what you find is that the Bardian potential during late time matter domination is related to the Bardian potential on super Hubble scales during early stages of the radiation domination epoch by a factor of 9/10. This will be discussed at length in a book like Doddelson, for instance. This is essentially that result. It is just arrived at by solving the Bardian equation on super Hubble scales. It's all wonderful. We know how the Bardian potential behaves. It has to be a constant on super Hubble scales, but we do not know what is Cg of k. As I mentioned, what I need to go back to the slide so many slides back. So essentially what we will do is as follows. Here we know there has to be a Cg of k that has to be determined. But we don't know what it is. We have introduced this epoch of inflation. what we will do is that we will bring these modes well inside the Hubble radius during the early stages of inflation. When these modes are well inside the Hubble radius, as I will discuss tomorrow, you can impose well-motivated initial conditions on your curvature perturbation. Okay, and you have to quantize this curvature perturbation. Remember, I said that the perturbations arose due to quantum fluctuations in the early universe. Until now, I've been just talking about classical perturbations, equations of motion governing the Bardian potential, its solution, etc. But the fluctuations arose because of the fact there were quantum fluctuations. The perturbations arose because there were quantum fluctuations in the early universe. What we will do is that we will elevate this curvature perturbation to a quantum field, impose well-motivated initial conditions, much like you impose initial conditions on quantum field theory in Minkowski space-time that you may be familiar with, you would have learned in a quantum field theory course. And once you impose these perturbations, we will evolve those perturbations, calculate essentially what is CG of K. We will just call it differently. We call it the power spectrum, scalar power spectrum and tensor power spectrum. We haven't discussed tensors. We will arrive at the equation of motion governing the tensor perturbations. It's relatively straightforward compared to the scalars. And we will calculate the spectrum generated, power spectrum generated in slow roll inflation, okay, the scalar and tensor power spectra. And another task I need to do before the end of the lecture tomorrow is, we will see that the scalar power spectrum generated during slow roll inflation is nearly scale invariant. It's flat. But if you want to generate enough number of primordial black holes in the early universe, what you need to do is that you have to have deviations from slow roll inflation. Before the end of tomorrow's lecture, hopefully what I will illustrate is that if you have deviation, certain types of deviation from slow roll inflation, particularly an epoch of ultra slow roll inflation, which was, Cristiano was one of the earliest people to discuss this scenario for the generation of higher number of, copious number of amount of primordial black holes. If you have that epoch, you can have a peak in the primordial spectrum, which can lead to enhanced formation of primordial black holes. That will be the scope of my lecture tomorrow. With that, I will stop here and I will be glad to answer more questions.